Okay guys, in this next video we're going to turn our attention to solutions, and so we'll describe some of the basic properties and definitions associated with solutions, and then we're going to learn how to calculate concentrations using the unit of molarity, and then there'll be some follow-up problems involving diluting solutions using the dilution equation. So a solution, as we've learned previously, is a homogeneous mixture of two or more substances. There are two different types of components to a solution. The first component, the solute, is the substance or substances that are present in lesser amounts. And the solvent is the substance in the solution that's present in the greatest amount. Typically, when we think of solutions, we think of aqueous solutions. That is a solute that's dissolved in water, but really there are all kinds of solutions. You can have gaseous solutions, such as air, or you can have solid solutions, such as a metal alloy. But we will typically be working with aqueous solutions when we're talking about solutions. So ordinarily, our solvent is typically water. The term concentration refers to the amount of solute that is dissolved in a given quantity of solvent. And we can use qualitative descriptors such as the word dilute, which means that you have a solution that has a small amount of solute, or you could say that you have a concentrated solution, which means that you have a large amount of solute dissolved in the solution. The term saturated means that you have reached the maximum amount of solute that a given amount of solvent can handle. If you go beyond that saturation point, what will happen as you continue to add solute is that the solute will sink to the bottom, and you won't see any more. You won't have any more solute being dissolved in the solution. So these are some definitions that we use typically when we're talking about solutions. And here in this slide, what we're going to do is quantify that idea of concentration. And so I'm introducing a new unit, the molar concentration, which is also called the molarity. I'm using the symbol C to represent this concentration. It's defined as the number of moles of solute per liter of solution. So here's the definition in an equation format. The molarity, C, is the number of moles of solute divided by the volume of solution. And you can use the molarity as a way of converting between moles of solute and volume of solution. So you can rearrange this equation in different ways. So here we're solving for the number of moles. It equals the molarity times the volume. So if you know the molarity of your solution and you know the volume of the solution, then you know the number of moles of solute that are dissolved in that given volume of solution. Conversely, if you need to deliver a particular number of moles and you know the concentration of your solution, you can calculate the volume you need to supply that number of moles. So you need to know this definition, and you need to be able to algebraically rearrange the equation in different ways to solve for an unknown quantity. Let's talk a little bit about the units of molarity. So since we are using liters of solution, the units would be moles per liter. Okay, so this is the typical unit for molarity. We recall from our previous discussions that a liter is equivalent to a cubic decimeter, so you can also express the units of molarity as moles per cubic decimeter. And we also use a special symbol, an upright M, to denote the concentration unit moles per liter. So 1 molar is equal to 1 mole per liter. One thing I want to point out is that the volume here in the definition of molarity, this is the volume of the solution, not the volume of the solvent. Those two things are actually different because the solute, when it's dissolved in the solution, it actually takes up some space. So the volume of the solvent that's used and the volume of the solution are not necessarily the same. Okay, so we want to keep that in mind when we're working with molarity. It's the volume of the solution, not the volume of the solvent. So in the next few slides, we're going to be working through some problems involving molarity. So in this example, we have a solute sodium nitrate that weighs 0.38 grams, and it is dissolved in a 50 milliliter solution. And we're simply being asked to calculate the molarity of the solution after that. So the definition of molarity, C, is the number of moles of the solute divided by the volume of the solution. In this problem, the volume is 50 milliliters, and we need to convert the grams of solute that we're given into the moles of solute. And we can do that directly on the formula. We can say that the number of moles of solute is equal to the mass of the solute divided by the molar mass. So we can modify the equation a little bit like this. So I'll take the, well, first we need to calculate the molar mass, right? I'm going to take sodium to be 23.0, nitrogen 14.0, and we have 3 oxygens, 3 times 16. So this will be our molarity calculation. So we'll take that to be 85.0 grams per mole. And then we'll plug that into this equation here. So 0.38 grams of solute divided by 85.0 grams per mole. And we'll divide that by 50.0 times 10 to the minus 3 liters. Notice I did the milliliter to liter conversion just right there on the paper. So running this through my calculator, I'm coming up with a molarity of 0.0894. That would be units of moles per liter. Or we could say it's a 0.0894 molar solution. Okay, so this is just a direct and simple calculation of molarity. In the next problem, this one is identical. We're just dealing with a different solute. So in this case, we have sodium chloride. We have a different mass and a different volume, but the problem is solved in exactly the same way. You need to calculate the molar mass of sodium chloride. You take the mass divided by the molar mass to give you the number of moles. You divide by the volume of the solution, and that will give you the molarity. So I'll leave that as an exercise for you. This problem is a little bit different. Okay, so we have an experiment which calls for 0.184 grams of sodium hydroxide, and we want to know if we have a 0.150 molar solution of sodium hydroxide, how many milliliters of that solution do we need to deliver that mass of sodium hydroxide? So here we need to rearrange the problem. We need to rearrange the equation and solve for the volume. So we can write the volume equals the number of moles of the solute divided by the molarity. So I've just taken this equation here and rearranged it, solving for the volume. Since we're not directly given the number of moles, we can also do the same trick where we plug in the mass and divide by the molar mass, substitute that in for the number of moles, and divide that by the molarity instead. So we will need the molar mass. We'll take that to be 23.0 for sodium, plus 16.0, plus 1.0 for the hydrogen. That gives us a molar mass of 40.0 grams per mole. And so we can substitute these numbers into this equation. We have 0.184 grams. We'll divide that by the molar mass of 40.0 grams per mole. And then we'll divide all of that by the molarity, 0.150. And I'm going to go ahead and plug this in as moles per liter. And so what we're going to get out of this, we're going to find that the grams cancel, the moles cancel, and we're going to be left with liters. And so I'm getting 0.030, we'll call it 7 liters. They want us to express that in units of milliliters, so we'll do that conversion on the fly, 30.7 milliliters, like that. Okay, so we need to be able to take the molarity equation and rearrange it and solve for the unknown quantity, volume in this case. Let's take a look at the next problem here. This one is similar. You're given a mass now of sodium chloride and the molarity of sodium chloride, and they want to know how many milliliters of that sodium chloride solution do you need to deliver 0.0958 grams. So it's solved in exactly the same way as this problem, but instead of using the molar mass of sodium hydroxide that we calculated, you would need to calculate the molar mass of sodium chloride and use these numbers instead. Okay, so I'll leave this as an exercise for you to try. Here we have a third variation of this problem. I'm going to try to save some paper and squeeze it in. It's probably a mistake to do this, but I'm going to try. How many moles of sodium chloride should be put into a 50 milliliter flask in order to give you a 0.15 molar sodium chloride solution? So in this case, we're being asked to solve for the number of moles. And so that would be equal to the concentration times the volume. So they give us a 0.15 moles per liter solution, and we have 50 milliliters of solution. I'm going to convert that to liters. You'll see the liters cancel out, and we're going to be left with moles. So I'm getting 7.50 times 10, I guess it should be just 7.5, times 10 to the minus 3 moles. And we're asked to calculate how many grams would that be. Well, we need the molar mass of sodium chloride, 23.0 plus 35.45 for chlorine. .4 grams per mole. To convert the number of moles to a mass, what we need to do is to multiply by the molar mass. So we'll have our 7.5 times 10 to the minus 3 moles, and we are going to multiply that by 58.4 grams per mole. The moles cancel, and we get 0.438 grams. Okay, so there are 3 different ways to rearrange the molarity equation, and you need to be comfortable with all 3 of them. Okay, so that's something you want to practice. Well, in this next slide, we're going to be talking about a different problem. We'll be talking about the dilution problem. And so this is a problem in chemistry that's very common. You have what's called a stock solution, okay, which means it's a solution that comes from the stock room, and it's a concentrated solution. So you might have, say, a solution of concentrated nitric acid, but you only need a dilute solution of nitric acid. So the idea here is that you will prepare from the stock solution, from the concentrated solution, you will prepare a dilute solution from that. And you can think of this as like watering down a drink, essentially. That's the idea here. In the slide, you've got a this blue colored solution here. Here you see that there's a darker hue of blue. Okay, and so this represents the concentrated solution. But if you add more water to it, okay, then you get this lighter colored solution. Okay, so this solution is more dilute than that one. And that's the idea. So we'll be taking a concentrated solution, a particular volume of a concentrated solution. We'll be adding water to it to create a more dilute solution. And these types of problems obey the dilution formula here, where Ci represents the concentration of the initial solution. Okay, so this is typically your stock solution concentration. Vi is the volume of that concentrated solution. The product of the concentration times the volume will equal the concentration of the final dilute solution times the volume of the dilute solution. And these factors are related in this way. The initial concentration is always larger than the final concentration when you add water to a concentrated solution. And the final volume is always larger than the initial volume that you started with. Okay, so that's how the equality works out. So we will work a couple of dilution problems. So in this example, we are given a concentrated solution of ammonia, okay, 14.8 molar, that's fairly concentrated, and they want to know how many milliliters of this concentrated solution are required to prepare 100 milliliters of a 1-molar ammonia solution. So notice that the concentration of the final solution is quite a bit smaller than the concentration of the initial stock solution. This is the volume, the final volume we want. We need to figure out what volume of this solution do we need to prepare this solution. So I'm going to start by writing out the dilution formula. And it can be helpful to write out what quantities you have and what quantity are you searching for. So in this case, we know that the initial concentration is 14.8 moles per liter. The initial volume is what we are trying to find. The final concentration that we desire is 1.00 moles per liter. And the final volume is 100 milliliters. So we need to solve this equation for the initial volume. So we're going to divide both sides by the initial concentration. That is going to give us this result here. And so we'll just plug in the numbers that we have. So we have 1.00 divided by the initial concentration of 14.8. And we're going to multiply that by 100 milliliters. And this is going to give us our answer in milliliters. And I'm getting 6.76. So you need to take a tiny bit of the stock solution, and then you will add enough water to equal 100 mils. And that's going to give you a new concentration of 1.00 moles per liter. The follow-up problem, part B, is identical to this one. You have the stock solution here, this 1.5 molar sulfuric acid, and you're trying to prepare 100 milliliters of 0.18 molar sulfuric acid. And so the question is, how many milliliters of this acid do you need to prepare this particular volume with that concentration? And so it's solved in exactly the same way. You'll be solving for the same unknown. The only thing that changes are the numbers that you're going to plug in. So I'll let you practice that. And then we're going to take a look at another dilution problem. Here, let's see if this one's any different. Yes, so in this problem we're solving for a different quantity. So we have 0.850 liters of a 5 molar solution of copper nitrate, and then it's diluted to a new volume of 1.8 liters. So the volume is being increased from 0.85 to 1.8. That's going to cause the initial concentration to decrease. And they want us to find the molarity of the new solution after we've diluted it. So again, I'm going to just go ahead and write down the dilution formula. It's very helpful to write the formulas that you're learning each time you solve a new problem. That way it'll help you learn the formulas. And let's look at what we have. Well, we've got an initial concentration of 5.00 moles per liter. We know the initial volume in this case, it's 0.850 liters. The final concentration, that's what we're being asked to find. So that's our question mark. And then the final volume is 1.80 liters. So we need to rearrange this equation and solve for the final concentration. Like so. We'll plug in the numbers. The initial volume, 0.850, divided by the final volume, 1.80. Run these numbers through our calculator. And I'm getting 2.36 moles per liter for the concentration of the diluted solution. Okay, and that makes sense, right? If you have a 5 molar solution and you add water to it, the concentration is going to decrease. The follow-up problem is identical to that one. You've got an initial volume, an initial concentration. You are increasing the volume to 500 milliliters. What is the final concentration of the methanol in the solution? So it's solved in exactly the same way as this problem, except for the fact that the numbers are different. So I'll leave that as an exercise for you to try. Here we have another variation of the dilution problem. Okay? So in this problem, they are asking us for what volume of 0.12 molar hydrobromic acid can be prepared from 11 milliliters of 0.45 molar hydrobromic acid. So let's write out the dilution equation and try to figure out what this problem wants us to do. Okay, so we'll just set up what do we have and what do we need. So the initial concentration is that 0.45 moles per liter. The initial volume is the 11 milliliters. The final concentration is the 0.12 moles per liter. And then it's the final volume in this case that they want us to find. So we need to solve this equation for the final volume. So I'm just algebraically rearranging it. And then we can plug in the numbers. And we'll multiply that by the initial volume of 11 milliliters. And that's going to give us our number. So I'm getting 41 milliliters out of that. It looks like this follow-up problem B is identical to that one. So I'm going to leave that as an exercise for you to try. And it looks like what volume. Here it looks like they're solving for the initial volume. It's very similar to It's very similar to this problem, only instead of solving for VF, you're actually solving for VI. So I'm going to leave, even though I haven't worked one that's exactly like this, I'm going to leave these two as an exercise for you to try. And then I think I have, yes, one more problem that I need to work on that's different from all of the others that we've looked at so far. This one is a little bit trickier. It's not too bad, but it's just a little bit trickier. Look at this question. How many milliliters of water do you need to add to 50 milliliters of a 2 molar stock solution of hydrochloric acid in order to get a 0.325 molar solution? So notice the question is a little bit different. How many milliliters of water do you need to add? And so that's the trick here in this question. Well, let's work the first part of this problem like an ordinary dilution problem. So I'm going to take CI VI equals CF VF. Okay. The initial concentration is this 2.00 moles per liter. The initial volume is 50.0 milliliters. The final concentration is the 0.325 moles per liter. And then the final volume is what we're trying to find. Now, the final volume will not answer the question, but we need the final volume in order to answer the question. Let me show you. So first, let's just find the final volume. So VF is going to be equal to CI over CF times VI. And I'm going to plug in the numbers. So we'll have 2.00 divided by 0.325 times VI. And so I'm getting 307, we'll round it up to 308 milliliters. That's the final volume of the solution. But that's not what the question asks. They want to know how much water do you need to add to 50 milliliters in order to get that final volume. So what we need to do is subtract 50 milliliters, the volume that we started with, and then the 258 milliliters. This is the milliliters of water that you need to add to the 50 milliliters in order to dilute the solution. So it's a slightly trickier version of the same problems that we've been looking at, but it's not too bad once you know to look out for the trick. So I think that is the last problem in this one. So I'm going to go ahead and stop this video right here.